All right, everyone. So welcome to the graduate seminar series. It's our honor today to have Dr. Xianming Shi from Washington State University to give us a talk on the graphene oxide as carbon-based nanomaterial that enables fly ash geopolymer concrete. Dr. Shi is currently a professor and the interim chair of Department of Civil and Environmental Engineering at Washington State University. He is also a fellow of ASCE, the American Society of Civil Engineers. He serves as the founding director of US DOT-sponsored National Center for Transportation Infrastructure Durability and Life Extension. And he's also the editor-in-chief of the Journal of Infrastructure Preservation and Resilience. So without further ado, please join me to welcome Dr. Shi for his presentation today.
Thank you. Thank you, Professor Zhang, for the opportunity. Thank you, everyone, for joining this webinar. And like Professor Zhang said, today the talk is about the use of graphene oxide as a carbon-based nanomaterial that enables fly ash geopolymer concrete. Basically, this is sort of a summary of the work we have done over the last 7-ish years, and also dealing with one patent technology, but I hope to drill down to some fundamental aspects as well. So, well, let me start from a little bit infomercial. Let me see, just how. All right, so first of all, I'd like to talk a little bit about the center I'm directing. Since it's relatively young, 2 years old, not too many people are familiar with the center. TRADLI, or National Center for Transportation Infrastructure Durability and Life Extension, basically is the only national center focused on this very issue, the durability of transportation infrastructure. And about 80% of our budget goes to research, but the rest goes to other priorities, including workforce development, education, diversity, tech transfer, and partnerships. And we have 6 interrelated thrust areas, ranging from asset management to non-destructive evaluation to addressing infrastructure resilience and materials durability issues and so on. Now, as you can see, this is a strategically assembled consortium of 11 universities led by Washington State University, and we have members representing different or diverse set of geological and climatic conditions, and they each bring some unique strength in research, workforce development, or outreach. Now, our shared vision is to develop cost-effective innovations and holistic solutions to enhance multimodal infrastructure durability. With the end goal being durable transportation infrastructure, we think there are best practices at every stage of the life cycle, starting from design and construction, then moving on to testing, monitoring, preservation, maintenance operations, post-event intervention, and rehab, repair, retrofit. Again, our focus is more on actually application of new materials and technologies. So that's kind of related to today's talk. And before I get started on the topic, I'd like to acknowledge my collaborator, Dr. Jin Zhong at Harbin Institute of Technology, who provides the graphene oxide for us. And we work very closely also on analysis of certain fundamental mechanisms. And my previous PhD students, Dr. Xu, Dr. Deng, and my current student, Dr. Li, well, Mr. Li, not Dr. yet. And our funding sources mostly from US DOT, Tier 1 UTC SASTIC, and National UTC TRADLI, and WSU Office of Commercialization. Actually, 3 of my students working on this line of research, each individually got scholarship from American Coal Ash Association Educational Foundation. We're really grateful for their support. And here are the companies who donated materials, my colleagues who assisted in the experimental work, and finally, here's the patent granted in 2020. Now, here's the outline of today's talk. I'd like to share with you some work, like I mentioned, in the last 7 years or so, starting from some introductory information about graphene oxide, which is a carbon-based nanomaterial, and then talk about the role of graphene oxide in cement hydration and then in fly ash-based geopolymer. And then I'll move on to graphene oxide-enabled geopolymer pervious concrete, and also what about its use, the use of this kind of binder in structural concrete, and then conclude with our contributions. Now, just to give you some idea about graphene oxide, it's a relatively new or emerging nanomaterial, which has been increasingly used in other industries, but in bulk applications such as asphalt and cement concrete, it's relatively new. Basically, this material features unique quasi two-dimensional layer structure with layer spacing approximately 1 nanometer. As you can see from the Fourier transformation infrared spectroscopy on the left and the X-ray photoelectron spectroscopy on the right, basically these nanoplatelets carry a lot of surface charges on it, and which, mostly include carboxyls, hydroxyls, epoxy, and ester groups. And those make the graphene oxide very active and actually reactive as well, and quite compatible with polymer matrices and water. For instance, we have played it in asphalt concrete, but that's not today's talk. So I'll focus on its compatibility with water and cementitious composites. So these nanoplatelets, again, when we make them, they were actually produced through a modified hammer method. As you can see, they look like dark ink. When you have a concentration of around 0.06% by weight, or approximately 6 grams per liter, they're actually dissolved in water. So it's like an ink. So there's no segregation or agglomeration. When you bump it up to 0.1% by weight, then you are dealing with an emulsion. So it's not fully dissolved, but still very good dispersion. Now, under the scanning electron microscope, you can see the bar here. The size bar here is about 10 microns, which, to put things into perspective, the diameter of a typical human hair is about 80 microns. So that's finer than hair. At that scale, you see a bunch of crumbled papers, basically. If we zoom in further to 1 micron bar, and you see more clearly, and then to even finer 500 nanometer or 0.5 micron size bar, then you can see, yes, it's a crumbled piece of paper. And keep in mind, the size is very small. It's roughly, a piece of 8 by 11 paper shrunk by 1,000,000 times. So, but it's kind of fascinating that at such a fine scale, trace amount of this material basically will dramatically change how the concrete behave, as I'll detail later. So again, here under the microscope, you can actually see the graphene oxide sheets if they're well dispersed. The thing is, the number of layers is crucial. Basically, if the number of layers exceed 5, you lose most of the magic for graphene oxide to behave like a nanomaterial. Instead, it will behave more like an expanded graphite. So to check that, we have tools to kind of estimate. One of the tools is the Z potential. In this case, in a near neutral pH aqueous solution, the Z potential is about minus 30 millivolt, which indicates these graphene oxide sheets carry a lot of surface charges, negatively, charged, and also the dispersion is very well. It's about single layer, so that's why they're highly effective. And also they have very high specific surface area, as you can see here. Now, what about its fundamental role in cement hydration? Is it simply a nanofiller, or it does more than that? Maybe more like a catalyst. So to answer that question, we examine a type of ordinary Portland cement or OPC paste with water cement ratio 0.35. And you can see by adding trace amount, in this case 0.02% by weight of cement, you're seeing on average about 30% increase for its 7-day, 14-day, 28-day compressive strength. And of course, the benefit to fracture strength is actually even a bit more because of this nanoplated structure, given a certain level of ability to absorb some fracture energy. So on the right-hand side, we got this scanning electron microscope type of image. In this mode, it's called BSE or backscatter image. You can see clearly the hydration phases, which has the CH, which is the polyandrite, and then you have CSH or calcium silicate hydrate gel. We see both the inner gel and the outer gel, and then you also see the unhydrated cement. Again, this is under really fine scale. As you can see, this is approximately 50 micron by 50 micron, again, finer than your hair. And the insight we gain from such a microscopic level is very helpful and sheds a lot of light on what's really going on. And another tool we use is XRD or X-ray diffraction. Basically, the OPC, once admixed with trace amount of graphene oxide, you see the formation of some new crystalline phases. One specific phase stood out is the silicon-rich turbomerite, and we'll talk about that a little bit later as well. So this specific phase contributes to the strength improvement as well. Now, if you look at this slide, it's pretty busy. At the bottom, again, on the left side, we confirm under a special instrument called EPMA, or Electron Probe Microanalyzer. At this very fine scale, we directly observed the presence of turbomerite. And the reason we are so sure is not just because of its shape, but also we did a 1D line scan over this crystal, and we found it's silicon-rich and there's significant presence of carbon. So that means there's coexistence of graphene oxide and turbomerite. And then similarly, if you look at figure B, in this case also is a graphene modified cement paste, you also detect another type of crystalline phase, which is gennite. Again, it's calcium rich, and also in that area, we see higher signal of carbon. Now, at the very top is figure A, which is the control group without any graphene oxide. This actually is detecting an unhydrated cement clinker, specifically tricalcium aluminate. So these tools at a very fine scale give us a lot of insight. Now, what about the quantitative analysis? We can actually use this tool to analyze, quantify the percentage of different phases. As you can see, overall, the conclusion is that the graphene oxide improves the hydration degree of cement. Well, if you look closer in the table, first of all, with graphene oxide, you're seeing less cracks and voids. You're seeing more silicon-rich hydrates and calcium-rich hydrates, and less CSH and polyandrite. Most importantly, you are seeing less unhydrated cement clinker. So in other words, the presence of this trace amount of graphene oxide actually altered the whole hydration, the composition of hydration products. Now, to examine it further, another tool is ICP-MS, or inductively coupled plasma mass spectroscopy. It's a very common tool used by chemists. So we extract the solution or the porous solution from the fresh cement paste at 20 minutes when the hydration was still very early in its age. And using this tool, you see some significant change in the porous solution chemistry. For instance, you see the graphene oxide significantly reduce the concentration of calcium cations and increase the concentration of aluminum and ion tetrahedrons. And again, the reason being, you know, the nanoplatelets of graphene oxide carry a lot of negative charges. So they're able to capture the calcium cation and repel those negatively charged aluminum and iron tetrahedrons. So this is very consistent with, with some previous knowledge by literature in terms of the interaction. Well, there are 6 different ways the graphene oxide could interact or capture calcium cations. Now, the new insight, of course, has more to do with what happened to the silicon and aluminum tetrahedrons. Traditionally, actually prior to this work published in the Carbon Journal, all the studies were indicating either the graphene oxide simply, you know, had a physical role, not a chemical reaction with the cement hydrates. But like we show here, actually, it's more than that. Graphene oxide also change the silicate and aluminate in the cement hydrates. So this is another tool called magic angle spinning, NMR, or nuclear magnetic resonance. Basically, the fundamental mechanism is that depending on the form of the silicate, for instance, at the top, you can see 5 different types of silicon, how the silicon atom would be surrounded by its neighbors, and they would dance basically to different rhythm in the nuclear magnetic field. So we can then identify that fingerprint, and using that characteristic peak, you know, the surface area under the peak, to indicate the relative signal strength or concentration of that specific phase. So we'll talk a little more about this in the next few slides. Now, for instance, on the left-hand side, you can see, you know, Q0 all the way to Q4, they basically indicate from a monomer, almost like an anhydrate cement clinker, all the way to a fully polymerized geopolymer with a network structure. And again, we can quantify how much percentage-wise, you know, each phase has in this cement hydration products or the mix of silicates. Same thing goes for the aluminum. On the right-hand side, you know, we can detect the different form of aluminum aluminates. So one interesting finding is quantitatively, you can see, again, Geo improves the polymerization degree of cement hydrates because you're seeing more Q4, Q2 silicates, and a significant reduction of Q0, which is anhydrate cement clinker, you know, from 7.9% to 0.2%. Again, different tools, of course, give you slightly different results. If you look back earlier, we probably had a different number for anhydrate cement clinker, but overall, they're telling the same story. Now, I guess armed with that knowledge, knowing that the graphene oxide is a functional additive or admixture, more than just a nanofiller, can we use it to benefit other types of binders? That's our fundamental hypothesis, where we believe, you know, graphene oxide could, you know, be used as a functional admixture for flash-based geopolymer. The fundamental motivation is that we want a greener cement and concrete industry. As you can see, cement industry contributes roughly 5% of the CO2 emissions. And then if you look at the numbers in the US, even though over the years we have improved this image, but still back in 2018, we're talking about roughly 36 millitons of fly ashes being produced, and only about slightly more than half of them were utilized. In other words, the other half basically end up in landfill. And the unintended consequences you would have is such as this type of air pollution you see on the top right, or accidents where like this coal ash spill in Tennessee contaminating valuable land resources. So the ideal situation would be diverting this type of fly ash from waste stream to value-added applications such as cementitious composites. But before we go there, traditionally, the industry has been exploring the use of fly ash as a partial replacement of cement for a long, long time, last 50 years. And the more recent trend is adding more than the typical 25 or 30% by weight of cement. For instance, we're dealing with high volume fly ash cement concrete here. This is one earlier work we did with 66% Class C fly ash and 34% cement. Even though the nominal water to binder ratio is relatively low, 0.27, our 28-day compressive strength was only 35 megapascal. So not ideal. And we try to understand why. Again, using this electron probe microanalyzer, we found that actually for the larger cement particles, when I say larger, they're actually only like, less than 10 microns in diameter. They actually did not fully participate in the reaction. So in other words, partially on the surface, about 1 or 2 microns, they became cementitious binder, but the rest of them basically are still working as an aggregate. So that's where we figured, well, maybe we need to add some activators. So that's where we started some statistical design experiments. In this design regime is called uniform design. You can see we had 27 groups and dealing with 5 factors at 3 levels. And we basically explored the use of water glass or sodium silicate, and then lime and calcium chloride and sodium sulfate as potential activators. One thing you might notice is we did not use any strong alkalis such as sodium hydroxide or potassium hydroxide, even though most geopolymers would do that. We avoided that because concerned about the leaching potential of those in the long run. And the other thing is we also aim to cure this type of geopolymer at ambient conditions, no pressure, no heat, no additional heat at least. Now, again, this is another imaging mode under the EPMA called SEI, or secondary electron imaging. It's very nice. You can see, a very fine scale on the surface of cement particles, fly ash particles. You can see thin layers of hydrates, similar to the stories we told before. In this case, of course, now we're dealing with 100% fly ash, not the 66%, but still the trend continues. However, once we add some activators, the image on the right, you see further hydration and formation of fibrous hydrates. And, so there's an improved degree of reaction. So what you see at the macroscopic level then is basically you're seeing the 28-day strength improve from 21 megapascal to roughly 34 megapascal. But again, that's still not enough. So what about we further add the trace amount of graphene oxide? Oh, let me see. Something's stuck here. All right. So again, actually, before I add the graphene oxide, you can see under another mode, which is the backscatter electron at a larger scale. Here the bar is 10 microns. You see the same thing. You see most of the fly ash being dissolved, but there's still some not fully dissolved. So they maintain the original spherical shape, and there's further room for improvement. So when we further add the 0.02% of graphene oxide by weight of fly ash, what happens is you are seeing additional increase from that improvement. So originally you had 21 to 34 megapascal. Now you bump it up further to 41 megapascal, another 20, 24, 25%-ish overall across the 7-day, 14-day, and 28-day. Now, again, these are confirmed under the microscope that, scanning electron microscope, there's further dissolution of the fly ash, and the cement hydrate, the fly ash hydrates look different. Now, one unintended benefit of adding the graphene oxide here is you can see on these 3 cylinders on the right, the very left one is the cement mortar, and the very right one is the alkali activated fly ash mortar. You see some leaching of the alkali, even though we didn't add the sodium hydroxide or potassium hydroxide, but even the water glass we add in still sort of leaching out. So that's concerning, and that doesn't look good. And then once we add the 0.02% graphene oxide, that problem disappears. So that's great. So this also gives us some indication that maybe the nanoplatelets, can help lock up some of the heavy metals, because that will be really beneficial, even though we haven't explored that yet. Now, if we want to understand the hydration process, especially in the very beginning, we use another tool, which is Raman Spectroscopy. We took the porous solution, and again, on the top, you see the activated fly ash paste. The bottom is the same paste, but we had trace amount of graphene oxide. We do see some difference. The main difference was the graphene oxide increased the intensity of Q3 silicate and quartz band at 24 hours. So that's desirable, because again, the more interconnected or the more cross-linked the silicates are, the more resistant to chemical attack and the better mechanical properties, conceptually speaking. So, but we also see over time, from 1 hour all the way to 24 hours, there's some change in the fingerprint of this porous solution, because you're basically going through a reduced pH over time, but we won't have time to dive into that. Now, again, I mentioned this EPMA, which is a very powerful tool. Yet another mode under the EPMA is called WDS, or wavelength dispersive X-ray. Now, what it can do is, if you select a small area of interest, say 50 microns by 50 microns, you can scan it once and you can get mapping of 5 elements. In this case, I only show 2 of them, which is calcium, silicon. We also did the sulfate, the sulfate and the aluminum and other things. But in this case, basically you are dealing with 500 pixels times 500 pixels. Each pixel has a quantitative number in terms of how much calcium, silicate, aluminum, and such. So with that, we can create such box plots at the bottom with, basically close to, 1 million data points. Now, you can see again, the trend is such that in the flash hydrates, you are seeing an slight increase in aluminum signal and significant decrease in calcium signal, and not much change in the silicate. That's a different story. Let's focus on the aluminum and the calcium here. The reason the calcium concentration in the flash hydrate decreased so much is because, again, going back to the fact the graphene oxide nanoplatelets would capture them from the porous solution. So when you have hydration products, they have actually less calcium in them. And similarly, you're seeing higher aluminum because, the graphene oxide nanoplatelets repel the aluminum tetrahedrons and push them into the solution, and you end up more of them in the hydrates. Now, silicate is a different animal because there are many different forms of silicate, and makes it really difficult to analyze. Now, the same story goes. For these data being plotted in a different way, then you can see the histograms here. We plotted the calcium to silica, silica to aluminum, and sulfate to calcium, and calcium to the combination of silica and aluminum. The reason being that the calcium cations, based on existing knowledge, they behave like network modifiers, while the silicates behave like network formers, and the aluminum or aluminates behave like network intermediates. So they play different roles. And in this case, one thing you can see is the significant shift, statistically speaking, some of these crucial elemental ratios. And one thing we detected, for instance, in figure C, is this apparent reduction or reduction in the amount of monosulfate formed in the hydrates because of the presence of graphene oxide. Another thing is, Okay. excuse me. The computer is being a little weird. Just a sec. All right. Another thing is these two ratios, figure A and figure D, indicates this formation of more silicon-rich hydrates. They actually are known to contribute to better mechanical properties such as stiffness and strength. Now, going back to the NMR, which is a very powerful tool, once again, we noticed or we revealed that the presence of graphene oxide increased the total amount of Q3 and Q4 silicate peaks from 47% to about 55%. Most interestingly, the Q4, which is the most cross-linked silicate, increased from 4.3% to 21.8%. In other words, the graphene oxide notably increased the cross-linking density of silicate, making it more of a geopolymer. Again, the traditional OPC hydrates will be more like a Q1 type, linear polymer. So that's a significant difference. Sorry. Now, we also see some interesting behavior of geo in inducing certain types of aluminate in hydrates, partially because of that mechanism we talked about. The geo repels the aluminum tetrahedrons because both of them are negatively charged. And actually, we think, this confirms also geo facilitated the dissolution of fly ash and push the aluminum ions into the CSH interlayers. And I think later we'll also slightly talk about this might be beneficial in terms of improved sulfur resistance of the concrete. Again, we haven't experimentally validated that yet. Now, what's interesting is also we try to use different tools to shed light on the same phenomenon, and they do confirm each other. For instance, on the left-hand side, in this case, the silicon NMR tells us we have decrease of Q2 silicate. And on the right-hand side is the TGA or thermal gravimetric analysis confirm that. And, because we're seeing less CSH gel content from the TGA curve. And also the calcite and polyline curve tells us the geo also increase the resistance of this fly ash geopolymer to carbonation. Now, the graphene oxide also induces the formation of some unique things like the ginnite we mentioned earlier. Again, all the different tools tell the same story. On the right-hand side, you see the figure B, which is a different way of plotting the millions of data points from that tiny area of 50 micron by 50 micron. You see some trend where there's some sort of grouping of aluminum calcium elemental ratio versus silicon to calcium ratio, which indicates the presence of ginnite. Again, we did observe it in figure C and in figure D through chemical analysis or the 1D line scan. Similarly, just a sec. I'm not sure why. Okay, so the graphene oxide also induced the formation of low quartz, which is a Q4 band or Q4 highly cross-linked silicate. Again, different tools. In this case, the XRD and the EPMA, both the morphology and chemical analysis, all of them tell the same story. What's interesting is also there's some difference between the fly ash hydrates and the cement hydrates. Like I mentioned earlier, the fly ash hydrates are more of a Q3, Q4. So if you look at the surface area under the peaks, actually it's dominated by network structures, while the cement hydrates, the CSH gel, is mostly linear polymer or chain structure. And if we look at the aluminum NMR, again, this is where we're talking about the fly ash hydrates, at least conceptually, seem to indicate they would be more resistant to sulfur attack than cement hydrates. again, that is yet to be validated. So to summarize, the role of graphene oxide is really a multifunctional admixture. It's more than just a nanofilter because it does chemically react and interact with the precursors in the porous solution of the either fly ash or cement paste, and then basically excludes the intermediates such as the iron and aluminum tetrahedrons, and consume the network modifiers such as the calcium cations, actually mainly the calcium cations, and then doesn't really significantly affect the network formers, which are the silicates. Well, one thing I should mention is if you look at the chemical composition of the fly ash versus cement, in this case, because we're dealing with class C fly ash, the lime content is relatively high, but still much lower than cement. Now, basically, if we look at the entire process of how we unlock the potential in the fly ash as a waste material or industrial byproduct, there are several steps. In the beginning, we use activators to dissolve the solid phase, facilitate the dissolution. Therefore, we generate or release a lot of network formers and modifiers. And then they will react with each other as precursors, sort of polymerize to a degree. And the presence of graphene oxide basically sort of coach the hydration process, affect the end result, and improve the degree of hydration as well as the degree of polymerization. Now, that's exciting. You know, we basically protected this knowledge, say, you know, now we invented a new and greener binder. So we want to put it to use. The first application is a pervious concrete. And of course, I'll get to structural concrete a little bit later. The motivation here is that we know pervious concrete or permeable pavement in general, both pervious concrete and permeable asphalt pavement are considered one of the very useful tools in the low impact development because they can help manage the quantity and quality of stormwater runoff. And you know, in arid or semi-arid areas, help recharge the groundwater. And also there are other benefits like, you know, you would have less traffic noise, less heat island effects, and less risk of slip fall when it comes to pedestrians walking on such pavement. So in other words, pervious concrete is a very green design for concrete pavement, but can it get even greener by replacing that cement with a greener binder? So that's our motivation here. So we developed 4 different groups. You can see cement and cement plus, you know, the trace amount of graphene oxide or fly ash, which is actually activated fly ash, and fly ash plus graphene oxide. You'll notice there's a slight increase in the second 2 groups in terms of water binder ratio because we had to achieve comparable workability. But in general, again, the graphene oxide in those modified groups are only 0.02% by weight of binder. Now, because it's a pervious concrete, we don't use, you know, the fine sand. So you have designed porosity or permeability. So they look like this. You know, the top ones are, you know, the 4x8 cylinders, and they really don't look that much different, whether it's, you know, graphene modified or whether it's a fly ash versus cement. The fly ash ones tend to be a little bit grayer or yellowish grayer color. But the thing is, all of them achieved acceptable void percentage based on ACI, you know, 18% to 31 or 32% is acceptable. And you can see the bottom left, all of them achieve reasonable void percentage. And we'll show later, this has a direct correlation with the infiltration rate. But here we also show they have a direct correlation with the density. Now, another concern was whether or not the graphene oxide-based materials will be.
Dr. Shi, I'm sorry to interrupt, but I think the slides are not advancing. We're still at the geo-induced formation of calcium-rich granite slides.
Oh, that's. Yeah, I'm not sure what happened. Can I stop share and reshare?
Yes, please.
sorry about that. Yeah, I'm not sure what happened. How about now? Which page are you seeing?
We're seeing developing pervious concrete with fly ash-based binder.
All right.
Yeah, it's now working.
Okay. All right. Sorry about that. And again, the bottom right, we're dealing with compatibility. This is a test, derived from supergyratory compactors. So there are indices which include the WEI and CDI. The WEI basically is an indicator of workability. As you can see, all four groups share similar workability. And CDI, however, indicate the amount of energy you need to compact the pervious concrete. And you can see the fly ash ones do require significantly more energy to compact them. The presence of geo further increased that amount of energy a little bit, but still they're reasonable, they're still highly compatible. Now, infiltration rate versus the void ratio, again, there's a direct correlation. You can see the R-squared 0.75. Now, infiltration rate on the left, you can see even the fly ash one or fly ash with geopolymer pervious concrete has significantly lower infiltration rate, but don't get too concerned about that, because when you look at the infiltration rate, they're still, close to 600 inch per hour. You are not dealing with that kind of heavy rain. Well, I'm not sure about Florida, but highly unlikely. My argument would be having a slightly lower infiltration rate may not be a bad thing, because then maybe you will have less challenge down the road. That's still an area to be further explored. I mean, in terms of clogging potential and such. Now, but at least, for now, it's within the range acceptable as a pervious concrete pavement. And if we look at compressive strength and split tensile strength, what's interesting here is the benefit of graphene oxide to the cement pervious concrete is significant, but not really impressive. Maybe you're talking about 30% improvement. But when it comes to the fly ash geopolymer ones, you are seeing more than 50% increase by this admixed 0.02% graphene oxide. That's very interesting. Now, the same trend goes for split tensile. Basically, they follow the same trend, and they have a correlation between the compressive strength and split tensile strength. And you see the failure mode on the bottom left. The left one is the cement pervious concrete. The right one is the geopolymer pervious concrete. They fail very similarly. Again, the color is slightly different. And if you look at this correlation between split tensile strength and compressive strength, it's within the range, ACI and others have reported. The red dots are all numbers. Now, what about Young's modulus and abrasion resistance? Again, on the left-hand side, at the bottom, you see the Young's modulus of the geopolymer ones are significantly higher, but still reasonable in terms of comparing against cement pervious concrete. Now, the degradation or the abrasion resistance through the degradation test at 90 days shows that you basically need the graphene oxide to make this geopolymer pervious concrete to be as good as the cement ones when it comes to, abrasion resistance. Excuse me. Now, what about resistance to salt scaling? We did this test using an STM C666, and interestingly, the fly ash geopolymer with graphene oxide is the only group that survived after 5 rapid freeze-thaw cycles in the presence of 3% sodium chloride. Arguably, this STM C66 test is too severe or too demanding for pervious concrete, because in the surface environment, oftentimes when you have freeze-thaw cycles, the de-isolating stormwater comes into the pervious concrete section. It will be infiltrated very quickly, so you won't be soaking this entire pervious concrete pavement in that condition for too long, unless you have a very poor design. You don't have comparable or reasonable infiltration rate of the base and sub-base, right? So in other words, the previous concrete design is takes a systems approach, not just the pavement itself. Now, the chemistry is such that the reason the graphene oxide modified geopolymer previous concrete did better than all the other groups is it changed the chemistry. Here, we're only using XRD or X-ray diffraction to tell the story, but we see that the graphene oxide improved the resistance of paste to carbonation during this salt skating process, where the integrity of the previous concrete, especially the paste, is compromised, and then you have higher risk of carbonation, but graphene oxide helped mitigate that. Now, also we're seeing, a refined structure on the left-hand side. Again, is the geopolymer without graphene oxide. This is after 5 rapid cycles of free sol in the presence of 3% sodium chloride. On the right-hand side is the one with graphene oxide. You can see that it's less heterogeneous. I wouldn't call it homogeneous, but less heterogeneous and less porous. The pores are much finer. So, salt skating is a very complex exposure. You involve both the chemical attack and the physical attack. So we try to separate the two. So we try to do the free sol without any de-icer and see what's going on. And again, the similar story is that the geopolymer previous concrete, behaved as good as the cement-based previous concrete, but still not as good as the geo-modified cement previous concrete. Because if you look at failure, the first 2 groups I mentioned failed at 144 cycles free sol, and the other one, the best one, is geo-modified cement previous concrete, failed at 162 cycles. And we use a non-destructive testing ultrasonic tool to capture, the loss of relative dynamic modulus. Now, like I said, we separate this physical one, then we look at the chemistry, the chemical attack. So we soaked the previous concrete in the salt solution, only going through, wet-dry cycles, not free sol. So in this case, very interestingly, the resistance to salt weathering, this is a different mechanism, right? Mostly a physical attack coupled with some chemical attack. Now you can see the green lines are the geopolymer ones, the ones based on, the previous concrete using the fly ash binder, and they perform much better. The reduction in dynamic modulus is much less than their counterparts with cement as the binder. So that's very exciting. And same thing, we detect the graphene oxide benefits the carbonation resistance, but also we saw that graphene oxide facilitated the formation of certain other hydrates like margarite or kynotobermarite and semi-crystalline CSH and CaSH gel, calcium aluminate silicate hydrate gels. Now, all right, so we already demonstrate, it works in previous concrete. We actually had implement some testing or demonstration slots on campus. It's been 3 years now, and they still perform the same or as good as the neighboring slot, which is cement previous concrete. Now, what about its use? The use of this geopolymer binder in structural concrete? You might have noticed that we had used a certain amount of calcium chloride as activator. So that means that binder would not be usable for a structural concrete with rebar or a concrete pavement with dowel bar, at least steel dowel bar. So, unless you use FRP bars or non-metallic bars. In this case, we further explore this technology and try to remove the calcium chloride and use some other activators. We're achieving slightly less compressive strength, but we adjust the rheological behavior and setting behavior And here the control is the one without graphene oxide. The target one is with the trace amount of graphene oxide. And we basically developed this as a rapid setting expansive cement without, sorry about that. All right. So again, this one is corrosion free, and so we can potentially use it for structural concrete. One application we're exploring right now is tube concrete. So with FRB tube, fiber reinforced polymer composite as the tube material, and inside you basically have this concrete. And we designed the binder to be an alternative or green alternative to expansive cement. And it's rapid setting, and hydration products are quite refined. So there's very little porosity. So that's a pretty good alternative to expansive cement. Now, again, we use the same tools to understand that hydration products and how the graphene oxide, even though it's used at a trace amount, 0.02% by weight of fly ash, significantly change the hydration chemistry and the final products. So one interesting thing is on the left-hand side, you can see the formation of certain layered structured hydrates. They're actually not your graphene oxide because graphene oxide is much finer. But that basically tells us the hydration process benefit from the template effect of the nanoplatelets. So the graphene oxide nanoplatelets guided or coached the formation of fly ash hydrates. And at the bottom right, we see that the water absorption is much reduced due to the admixed graphene oxide compared with the control group. So to conclude, here are our contributions. We demonstrate the beneficial role of admixed 0.02% graphene oxide in OPC and in fly ash geopolymer paste, mortar, and concrete. And the graphene oxide increased the 28-day compressive strength of cement and geopolymer paste by 29% and 23% respectively for water boundary ratio 0.35. And for the geopolymer purpose concrete, the benefit was much larger. For 7-day and 28-day compressive strength was larger than 50% increase. And georegulated the more ratios of these network formers, network intermediates, and so on, to form a different type of hydrate with improved strength. And the geo selectively altered the distribution of different hydration precursors and promoted the growth of low quartz and GenNet-like hydrates. And the UNAMA study showed geo improved the polymerization degree of fly ash geopolymer by increasing the total amount of Q3, Q4 silicates. Just to give you a summary that what we talk about today is mostly dealing with nanotechnology and purpose concrete waste utilization. We have been, over the last 15 years, doing a bunch of other things, all of which are trying to get to the greener concrete infrastructure. Now, with that, I welcome your questions. Sorry about the delay. Maybe I should.
Yeah, thank you, Doctor, for the wonderful presentation. Sorry, I'm extremely sorry for the interruptions. I think I may have, since we posted these informations online, we may have accidentally admitted some unwelcome guests. So hopefully these a little disruptions would not affect too much about today's seminar. Today otherwise wonderful seminar. So first of all, let's see if any of the students who are in the audience have any questions regarding the research presented here. Yes, I see one.
I have few questions, Professor.
Go ahead.
First of all, Professor, here the graphene oxide.
Okay.
So the graphene oxide is a
We may have to mute other folks.
So graphene oxide is a carbon-based material. So so when we are we using any activator, alkaline activator like sodium hydroxide or potassium hydroxide or sodium silicate, something like that?
Good. Yeah. You know, I probably mentioned slightly earlier. We do use a bunch of activators, right? In the previous concrete one, we use calcium chloride, sodium sulfate, and lime, and water glass, which is sodium silicate. But we did not use sodium hydroxide or potassium hydroxide. But in the later one, we basically removed the calcium chloride from the equation, so that it's chloride free and we can potentially use it for other applications.
Professor, another question. What is the actually source of the graphene oxide? Is it the source, the same source of fly ash, or is it a different source?
Very good question. It's made out of graphite through a chemical process called modified Hammer approach. So basically what it does is the strong acid will create an expansion force apart. Say if your graphene oxide is more like a book, again, a lot of crumbled paper sticking together. Now with this chemical approach, you're trying to disperse them into a single piece of paper. And again, like I said, it's about 1 million times finer than this piece of paper, but it's a little bit crumbled with wrinkles and with a lot of chemical groups on its surface, negatively charged, highly reactive, and highly active. But you're right. There are studies now. People are trying to grow graphene out of all sorts of things, like waste rubber or whatever waste materials. But that would be a different category. Again, the benefit of this graphene oxide is actually cheaper than graphene because it's a precursor to making graphene, and you don't need to get to graphene actually in this scenario.
Professor, I have another question. You claim that it reduces the carbonation. So how it contribute to reduce the carbonation, chemically or the material packing?
Right, very good question again. I think it's both. One way to look at it is we did see the hydrates are different than the control group, right? But also, the porosity is reduced. And then when you think further, nanoplates, they will significantly increase the tortuosity of diffusion path in terms of how CO2, carbonic acid, water get into the concrete, right? Because you're basically dealing with almost like, barriers. They have to get around it. They cannot go through it directly. It's a highly impermeable platelet. They have to go around it. So the tortuosity of diffusion path would be increased significantly.
Okay, Professor, my final question is, you prefer to use this material for a tube concrete. So are you expecting higher tensile strength? Like tubular structure usually actually hold that tensile strength or hoop stress. So are you expecting higher?
Right, that's a good question. Honestly, we haven't gone that far. We're still developing. So, but I think whatever challenge we may run into, we should be able to resolve. So yeah, we haven't done much. That's still ongoing PhD student work.
Okay, thank you so much, Professor.
Thank you.
Yeah, thank you. So I see another raising hand. Salam, please just unmute yourself and ask questions.
Thank you, Professor, for your presentation. I've worked on geopolymer like the past 3 years on slag fly ash geopolymers. Mm-hmm. And I have one question about the elemental compositions. In one of your slides, you showed calcium and, if I'm not mistaken, silicon, and like the box plots of them. Can you share this with us?
Are you talking about, sorry, are you talking about the chemical composition of fly ash versus cement, or? Yeah,
it was the fly ash versus cement and the effect of graphene oxide on them.
Right, let me try to, let me see how Sorry, let me see how I share. Just a sec. Okay, just a second. Actually, it might have been easier to share the other way. Just a sec. You're talking about this slide, right?
No, the slides where's the elemental mapping.
Oh, elemental mapping, yes.
Yeah.
You mean very colorful ones?
Yes.
With different colors. Yeah, the colors basically indicate different signal strength. Just a sec. Oh, this one?
Yeah.
Okay. So what, oh, just a sec here. It's kind of stuck. Let me see. All right.
Yeah.
So what's the question?
So here we see like an increasing trend of aluminum and a decreasing trends of calcium and silicon.
Mm-hmm.
So does this mean like the aluminum rich phases are much concentrated with graphene here?
No, the opposite. Basically, where there is graphene, they repel the negatively charged aluminum tetrahedrons away from them. So so those aluminum ions would enter the porous solution and participate in the hydration process and be found in the hydrates. So on the other hand, for the calcium, they basically were captured by the graphene oxide nanoplates and therefore did not participate in the hydration process. And therefore in the hydrates, you have less calcium. Does that help?
Yeah, it does. And I have one more question about the graphene oxide. Like, how much, like, is it cheap material or very expensive material? Is it abundant, like, to be used like as a fly ash?
Very good question. Whenever it comes to nanotechnology, there are always two questions. One, well, actually now it's three questions. One is cost, the other is toxicity, and third one is dispersion in matrices. Now, for cost, graphene oxide used to be probably very expensive. You could be talking about $50 per gram when this work was barely started 10 years ago. But now, over the last 10 years, I think now you can get this kind of graphene oxide about $2 per gram. Now, again, this cost will further drop if we demonstrate and implement bulk applications like the graphene oxide in asphalt, in coating, in concrete or geopolymer. Because if you look at raw material, it's graphite, it's abundant. And the process is very simple. And of course, advances are made every week, right, in the published domain. But the real issue is people haven't used this material in those bulk applications. So my experience, 20 whatever years ago, well, now probably 30 years ago, as a PhD student was at the time the Montemorronite nanoclay was sold by gram, and now you look at them, they're used everywhere, and they're sold by 25-pound cement bags, basically. So it's just a matter of improving the application scenarios so that you achieve economy of scale. Even if sold at $2 per gram, we did some rough calculations, still affordable in this application because we're only dealing with 0.2% by weight of cement. And you're achieving benefits in terms of strength and durability benefits. Yeah.
Okay, thank you so much, Professor.
Thank you.
Thank you. Is there any other questions? Okay. I think due to the time limits, I think we're just going to stop here. Please join me. Thank you. Thanks, Dr. Shi, again for this wonderful presentation.